Okay, we're gonna start up with some activated sludge, quick flashcards, just based on the activated sludge process and other things that are closely related to that process. So we're gonna start off and start with that. So, what is the activated sludge process? It is a biological wastewater treatment process that speeds up the decomposition of waste in the wastewater being treated. Activated sludge is added to the wastewater, and the mixed liquor, is aerated and agitated. After some time in the aeration tank, the activated sludge is allowed to settle out by sedimentation and is disposed of or wasted or reused, which is returned to the aeration tank as needed. The remaining wastewater then undergoes more treatment. So that's what is a snapshot of the activated sludge process. So another definition or another viewpoint is it a wastewater treatment process used to convert dissolved or suspended materials into a form more readily separated from the water being treated. Usually the process follows primary treatment using sedimentation. The process commonly is a type of biological treatment followed by secondary clarifiers that allow the solids to settle out from the water being treated. And the activated sludge process is also described as a mixed blend of microorganisms, 95% of which are a variety of mostly aerobic species of bacteria. So that's a key for what activated sludge is. 95% of those microorganisms are mostly aerobic species of bacteria. So that's something that's important to know. Also in the activated sludge process, we're going to talk about nitrification and denitrification, or some people say nitrification or denitrification. Either way, depends on where you're from in the United States. But nitrification, it is an aerobic two-step process in which bacteria oxidize the ammonia in water and wastewater into nitrite and then nitrate. The amount of oxygen required to oxidize the ammonia into nitrate is referred to as the nitrogenous BOD. So that's what nitrification is. It's a two-step process. So in order to nitrify, you have to denitrify as well. But the formula or the process to nitrify is NH4, which is ammonium or ammonia, to NO2, which is nitrate, to NO3, which is NO2, which is nitrite, to NO3, which is nitrate. So let me say that again. NH4 is ammonia, to NO2, which is nitrite, to NO3, which is nitrate. That's the steps of nitrification. So then after you nitrify, then you have to denitrify. How to denitrify, or what denitrification is the anoxic biological reduction of nitrate nitrogen to nitrogen gas. So the way to do that is NO3 is nitrate to nitrogen gas, which I believe nitrogen gas is NO2. So NO3 nitrate to nitrogen gas. That is denitrification, and you cannot nitrify without denitrifying. It's a two-step process. You need both to be complete, to have complete nitrification in a system. So we have that. Next, we want to talk about package plants. What is a package plant? So a package plant is a small wastewater treatment plant, often fabricated at the manufacturer's factory, hauled to the site, and installed as one facility. The package may be either a small primary or a secondary wastewater treatment plant. Typically, packaged plants use extended aeration in an activated sludge process. So they use extended aeration and activated sludge at packaged plants. Examples of packaged plants are a conventional activated sludge plant. So a conventional activated sludge plant for a packaged plant. Extended aeration is another one. Contact stabilization is another form of a packaged plant, or a complete mixed process as far as like the activated sludge is concerned, and how a packaged plant can be ran. Those different types of processes. Types of activated sludge processes. So you have in activated sludge, there's different processes that one can use. Here we're going to talk about high rate. So what a high rate activated sludge process does, it operates at the highest loading of food to microorganisms ratio. And the sludge age, which is how long the sludge is kept into the system, which we'll talk about that later. I don't want to get on that too quickly, but just pretty much how long sludge is held in the system. The sludge age, it ranges from 0.5 days to 2 days. So a half a day to 2 days is how long the sludge is kept in the system, or in the holding tank. It produces a lower quality effluent, so the effluent quality is not as good in a high rate system. In a high rate system, it is more easily upset than any other activated sludge plant or process. So that in a high rate system, because the highest, probably the highest food, or the food to microorganisms ratio, it takes in a higher strength of wastewater, which will upset a system because it's taking in higher concentrated wastewater, and with those flows, it could be coming from probably an industrial plant or something to that effect, and the process can get easily upset. So we have that going for us with that. And then the next thing is that deactivated sludge in a high rate system, it requires tighter control and frequent sampling and testing. So more testing, more sampling parameters, very, very tight in how things are ran in a high rate activated sludge process. So the next thing we want to talk about is the conventional, which the conventional is the most common type of activated sludge process plant. The food to microorganisms loadings or ratio is 50% lower than high rate plants. So they don't take in as much, or at least half of that they don't take in as like the high rate does. And the sludge age, or how much sludge is kept into the system, it ranges from 3.5 days to 7 days. So a little bit longer they hold the sludge in, because in a high rate, the return rate is very, very quick and very, 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 very much, versus a conventional where it's held in the system a little longer. So the return rate is not as bumped up as a high rate. So then the next thing is it produces a high quality effluent. So it's a very, very good effluent going out into the receiving streams, and can very, very be reflected of how the process is going. So as far as like I said, with the high rate, it's they're not easily upset, so it's not poor effluent going out or poor types of treatment or something. It is producing a high quality effluent. And then the next thing is, or lastly, is able to absorb some shock loads without lowering effluent quality. So with the high rate, it's more easily upset, which would lower the effluent quality, which that would make sense. But with the conventional, it can absorb some of those shock loads when it comes through with these industrial dumps and other things. And with that being said, it can absorb some of those shock loads without lowering the quality, so the effluent quality will still go out in a very, very good manner. Coffee so good. Now we're going to talk about the third and final types of activated sludge process is an extended aeration. So an extended aeration is often used in smaller package type plants. And so they're used in that kind of type of outfit. It's the most stable of the three process to do light loading. So it's stable because it doesn't take in a lot of food to microorganisms ratio. So they don't take a lot of, wastewater in as far as like the rate of it and everything. And then the sludge age is greater than 10 days. So since it doesn't take in a lot, it holds it the longest in extended aeration. So they hold the sludge a very, very long time in the system. And then the very last thing to note about an extended aeration process is that effluent suspended solids are usually higher. So they're usually higher with that, probably because of the sludge age is so long. The suspended solids are usually higher, and it would have that to be that because there's so much that's kept in the system. So now we're going to shift gears. Instead of talking about the activated sludge processes, we're now going to talk about the different modes of activated sludge and what kind of mode we're talking about. In the first mode we're going to talk about in activated sludge is the contact stabilization. Contact stabilization uses two aeration tanks. One tank is for separate re-aeration of the return sludge for at least 4 hours before it is permitted to flow into the other aeration tank to be mixed with the primary effluent requiring treatment. The process may also occur in one long tank. So it seems like with this one, with contact stabilization, it's one tank is for separate re-aeration and return sludge. So it's kind of like, to me, it seems like these tanks are like side by side or something, and they're doing their processing that and having that to be their process. So contact stabilization. The cross process. It is characterized by use of an aeration tank to aerate a portion of the return activated sludge, digester supernatant, and digested sludge to provide nitrogen to a nitrogen deficient wastewater. So that's the cross process. Step feed aeration. That's the next one that we're going to talk about. In step feed aeration, primary effluent enters the aeration tank at several points along the length of the tank rather than at the beginning or the head of the tank and flowing through the entire tank in a plug flow mode. So step feed is at different points within the tank that the effluent enters in, instead of like a plug flow where it starts at the head and goes through to the end. So that's what step feed is. It's just fed in different stages throughout the tank. A complete mix is the next thing, and that is characterized by the introduction of influent wastewater and return activated sludge throughout the aeration basin and use of a completely mixed aeration tank. So a complete mix is just it's just a completely mixed throughout the tank. So the whole tank has a good steady mix, and everything is mixed in well. That's how I would see it. It's kind of like probably when you want to bake a cake or something, or you want to, do something like that. You want to make sure all the ingredients are mixed so that it is a evenly flowed type of tank. That's what I would get it. The picture of is that all the ingredients has to be mixed in that to have a good process. Modified aeration. Modified aeration is characterized by a high food to microorganism ratio, low sludge age, a short aeration tank detention time, and high mixed liquor suspended solids. High rate aeration should be followed by other BOD and suspended solids removal process to provide secondary treatment. So modified aeration, that's what would be characterized in that type of process or type of mode of activated sludge. Barton-Foe process. Barton-Foe is a biological process which provides special conditions for both nitrogen and phosphorus removal. This system consists of 5 distinct reactors, which are respectively anaerobic reactor, first anoxic reactor, first aerobic reactor, second anoxic reactor, and second aerobic reactor. That's what the Barton-Foe process is. And it's for nitrogen and phosphorus removal, which that's a part of tertiary treatment, which is more advanced because not every wastewater plant removes nitrogen and phosphorus as much as some others do, depending on the class, the plant it is, and all of that. So that's Barton-Foe process. So now we're going to sequencing batch reactors, or SBRs. An SBR is a type of activated sludge system that is specifically designed and automated to mix or aerate untreated wastewater and allow solids flocculation or separation to occur as a batch treatment process. And the process goes like this. So when there's a SBR, the first thing it does is it idles. So it will idle, then it will fill, then it will react, then it will settle, and then it will draw. So idle, fill, react, settle, and draw. That's what a SBR, or sequencing batch reactor mode of activated sludge, does. All right, the next thing we got is a plug flow. And as I was talking about that earlier, when I think it was talking about step feed, comparing it to a step feed, a plug flow is a type of flow that occurs in tanks, basins, or reactors when a slug of water or wastewater moves through a tank without dispersing or mixing with the rest of the water or wastewater flowing through a tank. So a plug flow is like we was comparing it or contrasting it versus a step feed, is that a plug flow, it starts in at one end and it goes through to the other end, whereas step feed, like I said earlier, is the wastewater influent is injected in different points throughout the aeration tank. So we have that for a plug flow. It starts in at one end and goes to the other, and it doesn't disperse or mix with the rest of the water or wastewater flowing through the tank. Tapered aeration. So tapered aeration affects only the arrangement of the aeration devices in the aeration tank. In tapered aeration, the diffusers or aeration devices are spaced closer together at the head end of the tank to match the oxygen demand. So it's just more aeration seems like more aeration devices they're closer at the head end of the tank, so they can match the oxygen demand that's in the tank. An oxidation ditch. That is, the ditch consists of two channels placed side by side and connected at the ends to produce one continuous loop of wastewater flow, and a brush rotator assembly placed across the channel to provide aeration and circulation. An oxidation ditch. Kind of like people call it like either a washing machine, or I don't know if I heard it as a racetrack, but more like, it's like a washing machine type of flow to it, and that's what an oxidation ditch is in the mode of activated sludge. Selectors. A selector is a reactor or a basin in which baffles or other devices create a series of compartments. The environmental conditions or the food and lack of dissolved oxygen that develop are intended to favor the growth of certain organisms over others. The conditions thereby select certain organisms. And probably what they're talking about or alluding to is filamentous bacteria, maybe. But that's what a selector is. It's a reactor or basin, and creates a series of compartments. So we have that, and then high purity oxygen mode. That is characterized by covered oxidation tanks, use of high purity oxygen as a dissolved oxygen source, and short solid detention times. High purity oxygen. And then finally, to wrap up the mode section of this activated sludge processes or modes, is a membrane bioreactor. So a wastewater treatment process that uses a suspended growth bioreactor is typically found in activated sludge treatment processes, coupled with a membrane filtration process like a microfiltration or ultrafiltration. So these probably would have like some type of like a filtration, like maybe to how a ultrafiltration or microfiltration is, and like a membrane filtration, and wastewater goes through those things. They probably get fouled up every now and then, have to be taken apart and cleaned and stuff. But that's what a membrane bioreactor is. It's found in that. And so so now we're going to shift gears, and we're going to talk about the microorganisms that's in the activated sludge process. So microorganisms in activated sludge, they grow in two environments. Aerobic, which is a condition in which atmospheric or dissolved oxygen is present in the aquatic water environment. Or the second way that they grow anaerobic, which is a condition in which atmospheric or dissolved oxygen is not present in the aquatic water or environment. So they either grow aerobically or anaerobically. But that's how the microorganisms grow. So, how do microorganisms synthesize? They synthesize in two ways. The first is autotrophic, which if they're autotrophic organisms, plants and some bacteria, they use inorganic materials such as sunlight and carbon dioxide for energy and growth. That's what an autotrophic does. So they use inorganic material such as sunlight and carbon for energy and growth. Then the next way they synthesize is heterotrophic, which that's mostly what, humans and animals and other things are connected to, because when you're heterotrophic, organisms that use organic matter for energy and growth, such as animals, fungi, and most bacteria, are heterotrophs. So autotrophic is for inorganic things. Heterotrophic is animals and fungi and bacteria that use organic matter for energy and growth. So since we're on microorganisms, we're going to keep on driving on. And the types of microorganisms that we have here is bacteria. That's one of the main microorganisms in the activated sludge process. So bacteria is primarily responsible for removing organic nutrients from the wastewater. And the next thing about bacteria is that living organisms, they're microscopic in size that usually consist of a single cell. Most bacteria use organic matter for their food and produce waste products because of their life processes. So we have that. Bacteria are the main workers in the activated sludge process. So they're the ones that's actually doing all the heavy lifting when it comes to the treatment process, and when it's biologically being treated in the aeration tank and in the activated sludge process, is that the bacteria is doing most of the work, treating the wastewater. So bacteria stabilize organic material, substances from plants or animals. Bacteria make up roughly 90 to 95% of activated sludge biomass. So most of the sludge and the biomass that is created, 90 to 95% of it is bacteria. And there are 4 distinct phases of growth when it comes to bacteria. You have the lag phase, where cells grow, but not in numbers. Then you got the log phase, where cells grow in numbers. Then you have number 3, the stationary phase. The population remains constant because there are many cells dying as there are multiplying. And then the last stage is the death phase. There are more cells dying than there are multiplying. So they go through these 4 stages. And say them again. You got the lag phase, where they grow but not in numbers. You have the log phase, where they grow in numbers. Stationary phase, where there are more cells dying than there are multiplying. And then you have the death stage, where more cells are dying than they are multiplying. The stationary, let me go back. The stationary phase, where they remain constant because there are many cells is dying as there are multiplying. And then the death phase, more cells are dying than they are multiplying. So those are the 4 phases in cell growth or bacteria in activated sludge process. So now the next thing we're going to talk about is filamentous organisms. And a filamentous bacteria or an organism is an organism that grows in a thread or a filamentous form. So I've listened to other podcasts studying this stuff and everything, and they said like a filamentous, when you look under the microscope, it looks like a bunch of hair. It's like somebody took out a hairbrush and pulled out a whole bunch of hair, and then it's clumped together, and that's what filamentous organisms look like. And but they're not all bad, but a few filamentous organisms are necessary for producing a good flock. So you need good flock to form, the biomass and the sludge and everything, so the sludge can compact together and create a biomass. But you don't want too many of them, because sludge because if you have too much filaments, it will cause sludge not to settle properly, causing sludge bulking. So the sludge will bulk and rise up in the tanks and the clarifiers, and you'll see that it's not compacting properly because it's too much filaments. And filamentous bacteria thrive in low DO and low food to microorganism environments. So where the DO, dissolved oxygen, is very, very low, and low food to microorganisms ratio, so that means there's not a lot of influent wastewater coming in, and not a lot of food to the microorganisms, to the biomass to feed it. That's where filamentous organisms thrive and grow. The next thing I want to talk about is protozoa. Protozoa is another form of a bacteria, and they remove and digest dispersed bacteria and suspended particles. The types of protozoa present give us some indication of treatment system performance. So protozoa in the system will give us the indication of how the treatment is going. They are usually single-celled organisms and heterotrophs, or protozoa is. They may be used as indicator organisms, as their presence or absence indicate the number of bacteria in activated sludge, the degree of treatment, and effluent quality. So they're indicating how many that's in the system and what's happening as far as like treatment is concerned and the effluent quality of a system. They help in secondary clarifiers with predation of dispersed bacteria. And protozoa are classified by their structures and how they move. So there are different types of protozoa when it comes to the activated sludge process, and these are very important to know. But you have amoebas. They have little effect on treatment and die off as amount of food decreases. So when the food decreases, amoebas die off. Then you got flagellates. They feed primarily on soluble organic nutrients. Then you got ciliates. They clarify water by removing suspended bacteria. Then you got free swimming ciliates. They remove free dispersed bacteria. And stalk ciliates dominate at process end. So you don't want to see amoebas, but you definitely what you want to see is a mixture of some stuff, but you want to see more stalk ciliates than anything, because stalk ciliates show that you have a very, very good balance on your process and wasting and how much you're returning and stuff, and how much the biomass looks in the system. You want to see stalk ciliates in the process. So now we're going to talk about rotifers. Rotifers are also a bacteria as well. They're also called a metazoa. They're microscopic animals characterized by short hairs on their front ends. They are multicellular animals. And rotifers consume enormous amounts of bacteria. And they also feed on solid particles. Rotifers dominate longer A systems, including legumes. And it's going to go into what I'm going to say next. So they dominate longer age systems. And the next thing is that they indicate old sludge with the high MCRT and a turbid effluent. So when you see a lot of rotifers in the system, that means your sludge age is very, very old, and you got some old sludge that's been in that system a little too long, and might want to waste some of that out so you can have a better balance on your process. Get some fresh sludge in there, some fresh stuff in there. Next is the viruses, fungi, and algae. Viruses. These are parasites that it can only produce within a host cell. Viruses do not contribute anything to treatment. And they produce diseases such as hepatitis and other waterborne diseases. Viruses. Fungi. They're multicellular, they're heterotrophic, and eukaryotes. If I can say that right, I don't know if I said it, but they're present with pH changes and odor sludge. Aerobes or facultative aerobes is characterized fungi, and they grow well in low moisture, low nitrogen, and low pH environments. And they degrade cellulose and sludge, fungi. And then lastly, algae. They're either multicellular or unicellular, present with pH changes and odor sludge. Autotrophic eukaryotes, and produce oxygen through photosynthesis. So that's what algae does in activated sludge and bacteria and all these types of things. So we have that. Next is, what is endogenous respiration? Well, in activated sludge, an endogenous respiration is a situation in which living organisms oxidize some of their own cellular mass instead of new organic matter they adsorb or absorb from their environment. Endogenous respiration. So it seems like it's like they're eating their own cells in order to, it's just that they're absorbing their own self. So that's what endogenous respiration is. So next we're going to jump to what is BOD, COD, and CBOD. BOD is biochemical oxygen demand. And a biochemical oxygen demand represents the amount of oxygen consumed by bacteria and other microorganisms while they decompose organic matter under aerobic conditions at a specified temperature. BOD, in decomposition, organic matter serves as food for microorganisms and energy results from its oxidation. And BOD, it measures the organic strength of waste. So whenever somebody says BOD, you can think of it as food for the bugs or for the microorganisms, but it also measures the organic strength of the waste or the wastewater. And then lastly, a BOD test measures the amount of oxygen used by microorganisms, which that test is a BOD 5 is done in 5 days. And after 5 days, you can see how much oxygen was consumed by the bacteria or the waste to show how much oxygen was used. Chemical oxygen demand, or COD. It's a measure of the oxygen consuming capacity of organic matter present in wastewater. Chemical oxygen demand is expressed as the amount of oxygen consumed from a chemical oxidant in milligrams per liter during a specific test. Results are not necessarily related to the BOD, biochemical oxygen demand, because the chemical oxidant may react with substances that bacteria do not stabilize. A COD, it measures the concentration of a compound that can be oxidized. And something to always note about a COD, or chemical oxygen demand, is that COD value is always higher than a BOD. Always. So we got that going for us. And then carbonaceous biochemical oxygen demand is a subset of BOD. BOD results are based on DO depletion from both carbonaceous and nitrogenous actors in a wastewater sample. CBOD measures DO depletion from only carbonaceous sources. So carbonaceous biochemical oxygen demand only does things from a carbonaceous source. And that's what a CO or CBOD is. Okay. What is MLSS and MLVSS? So MLSS, or mixed liquor suspended solids, that's the amount of suspended solids in the mixed liquor of an aeration tank. And then MLSS are solids that either float on the surface or are suspended in the water or wastewater. That's what MLSS is, mixed liquor suspended solids. So the mixed liquor volatile solids are the amount of organic or volatile suspended solids in the mixed liquor of an aeration tank. The volatile portion is used as a measurement or indication of the microorganisms present. Volatile solids are organic or come from plants or animals. And then non-volatile solids are inorganic, such as grit, eggshells, and sand. So that's the difference between mixed liquor suspended solids and mixed liquor volatile suspended solids. What is MCRT and SRT? MCRT, or mean cell residence time, it's an expression of the average time, usually days, that a microorganism will spend in the activated sludge process. MCRT is the mass of the bacteria in the system. And then a desired MCRT for a conventional plant is 4 to 15 days. So the mean cell residence time is how much the mass of bacteria is held in a system. And in a conventional plant, which that's mostly a big majority of wastewater plants around the United States, they're going to hold a biomass or mass of bacteria in the system for 4 to 15 days. That'll be the snapshot of mean cell residence time. Solids retention time. So that is a measure of the length of time solids in the aeration tank have been retained in the aeration tank. So solids retention time can be viewed as the total mass of solids in the treatment system. So they seem like they're talking about the same thing, but they kind of slightly different. But you got MCRT and then SRT. And it's about something being held in the system, sludge or a mass of bacteria. So, pin flock and straggler flock. So flock is particles that clump together to form a cluster because of the actions of bacteria, biological flock, or coagulants, chemical flock. So you have that is flock. Then you got pin flock. Pin flock is a very small flock the size of a pinpoint that does not settle out of the water in a sedimentation tank or clarifier. And then lastly, we have straggler flock, which is an indicative of a young sludge which tends to settle slowly. This type of flock consists of light, fluffy, and buoyant particles. Straggler flock. Foaming. Foaming is unstable foam. Is usually easier to control and is caused by nutrient deficiencies from the dewatering process or polymer overdose. Persistent foams are caused by process imbalance due to the growth of filaments or nocardia foam. And persistent foams are hard to control because they are corrected by the activated sludge plant process. Whatever the cause, there is a definite relationship between foam buildup and the number of suspended solids and airflow in the aeration tank. Stable, dark tan foams indicate the MCRT is too long. Old sludge or old sludge age, and the MCRT is probably greater than 9 days. The solution is to increase sludge wasting to reduce MCRT. Thick billows of white sudsy foam indicate low MLSS or low food to microorganisms ratio. Solution is to decrease sludge wasting to increase MLSS and MCRT. This typically happens during the startup of an aeration tank. So when you're starting up an activated sludge plant and you get that white sudsy foam, it's probably a startup of a plant. You got young sludge. You don't have much stuff that you're treating, or you're oxidizing probably like detergents or something. It's just not, you're just starting it up, so you don't have nothing built up for the activated sludge process. And then lastly, if it's very dark or black foam, indicates anaerobic conditions due to insufficient aeration or an industrial waste with a dark dye has entered the plant. The solution is to increase aeration and ensure a minimum DO of 1 milligram per liter into waste and waste to increase the MLSS concentration. Okay, I think I'm going to give it a rest right there, and then I'll pick back up a little bit later and pick back up. All right, good afternoon, everybody. We're back at it with the second part of the Activated Sludge audio flashcards. We're going to finish up today and get this all together and in place. So we're going to start this second part with high organic waste loads. We're going to talk about that and some things to note and understand about high organic waste loads. And when you have a high organic waste load, the first thing to recognize and realize is that the focus is to maintain microorganisms' treatment efficiency. So you want to have that treatment efficiency when dealing with high organic waste loads, because there is a lot of probably industrial, stuff in there, or that might be more inorganic, but excuse me, that's probably wrong what I just said. But the high organic waste loads is your treatment has to be very good, because when you have a high load that's coming in, you have to have a balance in order to treat the high organic waste load. Your return activated sludge rate must be increased to provide more microorganisms for treatment of the waste load. So the more high organic waste comes in, your return activated sludge rate must be increased. So you have to keep up with, the more food that's coming in, you have to be able to treat and maintain that RAS, or that return activated sludge rate, so that it can be able to provide more microorganisms for the treatment of the waste load. So the food coming in, that's the high waste load. So it's more food, but you have to send out more bugs in order for it to eat that food and consume that waste. Also, your return activated sludge rate, it must be gradually increased so the aeration tank and the secondary clarifier are not hydraulically overloaded and the solids loading rates are not exceeded. So when you do a return activated sludge rate, it has to be increased so that it can, balance the hydraulic loading. So you don't want things to be overloaded in the aeration tank. You want it to be uniform, and everything is has a good level to it when it comes to return activated sludge rate. You want to ensure proper DO levels are maintained. You want to keep the dissolved oxygen in the aeration tank with these high organic waste loads maintained, because when the DO level is maintained and kept, then things won't go septic and things won't go rotten or whatever word you want to use. It won't start to die and be dead. It'll keep everything alive and maintained, because the microorganisms, they feed on the aeration process of an activated sludge. So you want to keep them alive. You want to keep them moving. It's just like a human being. Like, we have air to breathe. We eat food. We digest. We waste out and do different types of things. So it's kind of like a human biology. It's the same thing with microorganisms in an aeration tank. And you have to ensure those proper dissolved oxygen levels are maintained in order to keep the process going. So, and also, if a waste load is high, additional nutrients may be needed to be added. So, things like, nitrogen and, phosphorus and all those types of things, those types of nutrients. Because of a high waste load, you want some nutrients to go out into the receiving stream. Not very much. You want to keep it at a regulated level, but you want your receiving waters to have some nutrients in them, because it helps the ecosystem and everything in the receiving streams and the bodies of water and everything out there. It keeps them in a proper uniform way. So if a waste load is high, additional nutrients need to be added, because you want nutrients to be in the water. You don't want it to be nutrient deficient in the water into the receiving streams. And seeding sludge, lastly, seeding sludge may be needed for high organic waste loads. Comparing microscopic results. That's what's next. And the activated sludge process never reached a steady state due to changes of influent wastewater flow, strength, and constituents constantly changing. So that's what it is about comparing microscopic results. If issues arise in the process and everything looks normal, comparing microscopic observations with laboratory process data with past microscopic results. So when it's dealing with microscopic results, if issues arise in the process and everything looks normal, comparing those observations, you got to compare them with the laboratory process data and past microscopic results. So you got to compare things. Laboratory process data, process control guidelines, and flow streams should be plotted on graphs, which will enable you to quickly observe upward or downward trends. So you have to have that data readily accessible and available for you to look at, so you can see what kind of trends the wastewater and the process control and everything has been going, and how it's been flowing through the chart. So you have to see those things. and know those things. Also, we have past microscopic results. When comparing past microscopic results, the comparison should be made within the immediate past with the immediate past or the same time as last year. So within a past month, you have to look at those results and see how it's like a snapshot of what's been going on in the system at that time, so you can look at those past results. Next, we're going to talk about nutrient removal systems. And we have different types of those nutrient removal systems. But one big one is an ammonia nitrogen removal. So an ammonia and nitrogen removal, we have to look at breakpoint chlorination. And breakpoint chlorination is accomplished by adding chlorine to wastewater in a sufficient amount to oxidize ammonia and nitrogen to nitrogen gas. And then the pH is decreased, causing acidic conditions. Addition of caustic soda or lime is needed, but adds to dissolved solids in wastewater. So we have that with breakpoint chlorination, and dealing with that in wastewater. It's a little bit different in wastewater than it is in water treatment, but it's definitely has the same goal, is that you want to have some type of residual to fight against pathogens and disease-causing organisms. And then it says right here, it says to oxidize the ammonia, nitrogen to nitrogen gas. So chlorine is an oxidizer, and it oxidizes ammonia, nitrogen to nitrogen gas to do that. Ion exchange. That involves passing an ammonia-laden wastewater through a series of columns packed with a material called clinoplatinolyte. The ammonium ion adheres to or is absorbed by the clinoplatinolyte. This process converts ammonium ions to nitrogen gas, which is released in the atmosphere. So ion exchange is another way, or another type of ammonia nitrogen removal system that does that type of treatment of process treatment. Ammonia stripping, a biological treatment process that uses physical process called desorption or stripping. Wastewater is made alkaline by the addition of lime. Because of this, ammonia is induced to leave the water phase and enter a gas phase and enter the atmosphere. So ammonia stripping is another way of ammonia and nitrogen removal and nutrient removal systems. Overland flow. Overland flow is wastewater to be treated is applied to grass-covered slips by sprinklers or to the land surface through ports and pipes at evenly spaced intervals. The wastewater flows through water-tolerant grasses to a collection ditch. The microorganisms that live in the grass reduce BOD and cause both nitrification and denitrification to occur. Phosphorus removal. So you got things about phosphorus removal is Barton-Foe process, a biological process which provides special conditions for both nitrogen and phosphorus removal. This system consists of 5 distinct reactors, which are respectively anaerobic reactor, first anoxic reactor, a first aerobic reactor, second anoxic reactor, and second aerobic reactor. Phosphorus stripping. What is phosphorus stripping? Its effluent is run into a tank and dosed with a product known as a precipitant, such as alum or lime, which combines with phosphate in solution to create a solid, which then settles out and can be removed. A luxury uptake. A luxury uptake of phosphorus is a biological treatment process whereby the bacteria usually found in the activated sludge treatment portion of the secondary wastewater treatment plant are withdrawn to an environment without oxygen or anaerobic. When the bacteria are faced with the situation of apparent death, the bacteria release phosphorus from their cell structure in large quantities. Phosphorus can then be removed and disposed of by using lime for settling, like the previous discussed lime clarification process. After the bacteria have released their phosphorus, they are placed back into an ideal environment with oxygen and food. In this environment, since the bacteria are lacking in phosphorus in their cell structure, the first thing they take in is phosphorus. Suspended growth reactors. That's another ammonia and nitrogen removal or nutrient removal. I think that's what I said, nutrient removal systems. A suspended growth reactor is a conversion of ammonia into nitrite, then nitrate. Suspended growth reactors are normally in aeration basins, so it's pretty much an activated sludge tank or an aeration basin. The basin must be large enough in the MCRT, long enough, usually 4 days, to allow slow-growing nitrifying bacteria to grow. Organic material and excess nutrients in the wastewater are removed as these flocks move through the water. Examples of suspended growth processes are a conventional or plug flow aeration system, which we've talked about that earlier in the other part of the activated sludge audio flashcards. But conventional or plug flow aeration systems are two different types of activated sludge systems. And so we have those. Then we have the complete mix activated sludge process, in which everything is completely mixed and is uniform throughout the activated sludge tank or the aeration tank. Contact stabilization is another one, and that is where two tanks are used in the activated sludge process, and that's I need to study up on that a little more. But yes, the contact stabilization is with two tanks that deal with two aeration tanks that deal with the activated sludge process. Extended aeration is aeration for a longer period of time, to where it has a very, very low food to microorganisms ratio, but extended aeration is probably more so like things like oxidation ditches and stuff that has a very, very low food to microorganisms ratio, but it's keeping everything in suspension for extended aeration for a longer period of time, which gives everything a longer sludge age and those type of things. And then the step feed activated sludge process is where incoming influent wastewater is diverted into different portions in different places in an aeration tank. So it's in different steps that is given. So it's not like a plug flow where it comes in, a slug of wastewater comes in at one end and then goes through and goes out to the other end. It's a step feed where it's injected or introduced in different portions of the activated sludge aeration tank. So then we have issues in the activated sludge process, which is rising sludge. That is a very, very big issue. And rising sludge occurs in the secondary clarifiers of the activated sludge plants. When the sludge settles to the bottom of the clarifier, it's compacted and then starts to rise to the surface, usually a result of denitrification or anaerobic biological activity that produces carbon dioxide or methane. So when you have gas bubbles, or like it says, produces carbon dioxide or methane, and it's an anaerobically biological activity that causes these gas bubbles to get into the sludge, and the compacted sludge, and then it starts to rise to the surface of the clarifier, which is denitrification. So that's rising sludge. That's an issue, and that's a problem in the activated sludge process. And then we have sludge bulking, not sludge, sludge bulking, which is caused by the sludge not settling properly, typically from filamentous organisms. So rising sludge is usually by denitrification and gasification in the sludge of an activated sludge process. And then sludge bulking is caused by sludge not settling properly, and it's typically from filamentous organisms, which are these organisms look like a bunch of hair that was pulled out of a hairbrush. And filaments are not all bad if it's just a small portion of them, because they help the sludge compact and make a biomass and create that sludge blanket at the bottom. But when it's too many of these types of organisms, then it causes the sludge to not settle properly, and then it causes issues where the sludge will bulk in the aeration tank. Sludge volume index. That is a calculation that indicates the tendency of activated sludge solids or aerated solids to thicken or become concentrated during the sedimentation thickening process. And the SVI is calculated in the following manner. So, to calculate an SVI, you need to allow a mixed liquor sample from the aeration basin to settle for 30 minutes. Determine the suspended solids concentration for a sample of the same mixed liquor, and then calculate the SVI by dividing the measured or observed wet volume of the settled sludge by the dry weight concentration of the MLSS in grams per liter. Next, we're going to talk about return activated sludge flow rate control. So the return activated sludge flow should be controlled at the minimum rate, which holds the solids blanket between 2 and 13 feet below the clarifier weir elevation. If the blanket is more than 13 feet down, the return activated sludge and the waste activated sludge concentrations will be low, and turbulence in the clarifier will likely be unnecessarily high. And lastly, the flow rate should be changed to match the strength of the incoming wastewater. And that, everybody, is that is the second portion of the activated sludge audio flashcards. And so this is an end to this recording.